Okay, so hi everybody, welcome back. Today we're going to be going over some of the practice problems from the chapter 14, 13, and 17 lectures. So we've actually covered all the material from those lectures that I wanted to get to. So what we're going to do here is just go through some of the practice problems at the end of each one of those lectures to help you prepare for the test. So this is the chapter 14 lecture on oscillations. We have a number of problems here at the end of the lecture, but let's try this one out. The system shown below consists of a 175 gram mass connected to a spring with the force constant K is equal to 15.0 newtons per meter. The surface that supports the mass is frictionless and there is no air resistance. So at t equals 0, the spring is compressed by a distance 4.50 centimeters from equilibrium, and the velocity of the mass is 20.0 centimeters per second in the positive x direction. So the spring is compressed by 4.5 centimeters, and it's moving this way to the right at 20 centimeters per second. Now, what we're going to do is, based on this data, we're going to find the equation x of t for the motion of this block based on this general solution, which is x of t is equal to a cosine omega t plus phi. So the goal for this is going to be to find the amplitude a, the angular frequency omega, and the phase constant phi. That will give us the solution for the motion of this block. So pause the video for a second, see if you can get this, and then we'll go through it together. Okay, so the general solution for this simple harmonic oscillator is x as a function of time, so that's position x as a function of time t, is equal to a, that's the amplitude of the motion, times cosine omega t plus phi. So the goal of this problem is to actually calculate numerical values for those three constants, a, omega, and phi. So the easiest one is probably the angular frequency. Remember, we're dealing with a mass spring system with no damping. That means we're not losing energy to friction or air resistance. And so when that's the case, the angular frequency omega is going to be given by the square root of k divided by m, where k is the spring constant, 15 newtons per meter, or equivalently, we can say kilograms per second squared. Okay, that's the same as a newton per meter. The mass is 175 grams, or 0.175 kilograms, which gives us omega 9.258. The units will be radians per second. So we'll run around that to 3 sig figs, so 9.26 radians per second. Okay, so that takes care of omega. Now let's try to find the amplitude. So there are different ways you can go about this, but I'm going to use conservation of mechanical energy. So this is the idea that the total energy of our oscillator is going to be conserved because there's no friction or air resistance acting on it. So the total mechanical energy E is the sum of the kinetic energy and the potential energy. So we can make some substitutions into that. You'll recall one of the results from the lecture is that the total mechanical energy can be expressed as 1/2 times Ka squared. So that goes in for E on the left side of the equation. But then kinetic energy is 1/2 m times V squared. And then potential is 1/2 K times x squared. So what we're going to do for V and for x is we're going to plug in those initial values we were given. And that way we can solve for A. So if we multiply through by 2, divide through by k, we have a squared is equal to m over k times v squared plus x squared. So the amplitude is the square root of that. Again, the mass is 0.175 kilograms. The spring constant is 15 kilograms per second squared. We multiply that by the initial velocity that we were given. So that was 20 centimeters per second, or 0.200 meters per second. So we converted from centimeters to meters, and we square that v. We were also given that the initial value of x is 4.5 centimeters, or 0.045 meters, and we square the x value. So this will give us an amplitude in units of meters, which comes out to 0.04992 meters. And we'll keep 3 sig figs, so that works out to 4.99 centimeters. Okay, so we have omega over here. We have A. So we have 2 of the constants we wanted to find at the beginning. The last one is the phase angle. So let's see how we can find the phase angle. Well, this is phi in the equation. And what we can do is take our general formula for x as a function of time, but plug in 0 for the time. So x at time 0 is going to be equal to, okay, if we go up here to the general form, it's a times cosine omega t, but if t is equal to 0, omega t is just 0, and all we're left with is phi inside the cosine function. So x at time 0 is equal to a times cosine of phi. So we can rearrange this to try to solve for phi, because cosine phi is equal to x0 divided by a. You have to be a little bit careful here. Initially, the spring is compressed, which means the x initial is negative. So we have negative 0.0450 meters for the initial x value, divided by 0.04992 meters for the a value. So meters cancel out, we just get a number, and that number is minus 0.9014 with 3 sig figs. Okay, so if you take this and you just plug it into your calculator by doing the inverse cosine, if you say phi is equal to the inverse cosine of negative 0.9014, you're going to end up getting, your calculator will spit out 154.3 degrees. Again, we're keeping 3 sig figs on that. So this is what the calculator gives. But that's not the end of the story. We have to go to the unit circle to really see if we're getting this right. So remember, the unit circle looks like this. We have the xy plane, and then we draw the unit circle with the center at the very origin. And remember that cosine of an angle is equal to the x coordinate on the unit circle. So here we're saying if cosine of phi is equal to negative 0.9014, that the x coordinate is negative 0.9014, like this. So what I'm trying to get you to see here is that there are two angles that could work. This one right here is 154.3 degrees. That's what the calculator told us, positive. But the thing is, we could also be down here, and it would work just as well. That would be the negative angle, negative 154.3 degrees. So we really don't know which one is correct, okay? The two possibilities are phi equals positive 154.3 degrees or negative 154.3 degrees. We have to test these out to see which one is right. And the way we'll do that is by looking at the velocity. So if x as a function of time is equal to a cosine omega t plus phi, then the velocity as a function of time, that's the derivative of x, the derivative of position with respect to time. So cosine goes to negative sine, and then we have to pull out a factor of omega by the chain rule. So we have minus a times omega sine omega t plus phi. That's our velocity. Now if I plug in 0 for the time, velocity at time 0 is minus a times omega sine of phi. So here's the idea. We're given that this initial velocity, the velocity at time 0, is positive. So we need it to work out to a positive number to match the initial conditions we're given. But if we test out phi is equal to positive 154.3 degrees, okay, if you actually plug that angle into this function here, sine of 154.3 degrees is positive, but there's a negative sign out front. So overall, your velocity at time 0 is going to be something negative, okay? Something less than 0. On the other hand, if we say phi is negative 154.3 degrees, again, if you plug in sine of negative 154.3 degrees, you will get a negative number. But that negative sign will cancel out with this negative sign out front. So your velocity at time 0 will be positive. Again, this is correct. We want the velocity at time 0 to be positive. We don't want it to be negative, which is how I can determine that the negative angle was actually the correct choice. So notice the calculator gave us the wrong answer. It's actually the negative angle that's correct. So the last thing we'll do here is take that angle and convert it to radians. I have minus 154.3 degrees with 3 sig figs. There are 360 degrees in every 2 pi radians. So degrees cancel. Now we're in radians. And this works out to negative 2.693 radians. And then we'll keep 3 sig figs. So the final answer is x as a function of time is equal to the amplitude, 4.99 centimeters, times cosine omega, which was 9.26 radians per second, times t, and then minus 2.69 radians, like this. So notice if I have radians per second for omega, I'm going to also want to have radians for my phase angle phi, just so the units are consistent. And so this is the this is the solution for this specific case. Plug in any value of t, and the position of your oscillator x is going to pop out. So this describes exactly how the oscillator is moving at any given time. Okay, so here's another example from chapter 14. So you crash land your spaceship on a mysterious planet, and you want to figure out g, the acceleration due to gravity on the surface of that planet. So fortunately for you, you brought a stopwatch and a simple pendulum. The pendulum is just a 75 centimeter long string tied to a 1.5 kilogram mass. So you watch the pendulum oscillate back and forth, and you measure the period to be 1.52 seconds. So the question is, what is the value of g in units of meters per second squared? So we're going to assume here that there's no air resistance as the pendulum swings. So pause the video, try to work this out, and then we'll go through it together. So in lecture, we derived the angular frequency of a simple pendulum. And that was given by omega is equal to the square root of g divided by L. So it only depends on these two numbers, the acceleration due to gravity, which on Earth would be 9.8 meters per second squared, but it's something different on this planet. And then L is the length. We'll also remember that the period of any simple harmonic motion is given by capital T. That's how long it takes to undergo one full cycle. That's 2 pi divided by omega. So this would be 2 pi times the square root of L over G, so we have to flip the fraction. If we square both sides, we have T squared is equal to 4 times pi squared times L over G. We're looking for G. G is equal to 4 pi squared times L divided by T squared. Okay, so we're ready to calculate because G is equal to 4 pi squared times the length, which is 75 centimeters or 0.75 meters. And then T is the period, which is 1.52 seconds, which we square. So unit-wise, this is working out in meters per second squared. And what you'll get is 12.82 meters per second squared. Round that off to 3 sig figs to get 12.8 meters per second squared. So by measuring the period of this pendulum, you're able to find out g, the acceleration due to gravity. Okay, that's the idea behind this one. Okay, so here's another one to think about. You set a simple pendulum in motion by displacing it 7.5 degrees from the vertical and letting it go. So at the start of the motion, the angle between the string and this vertical line is 7.5 degrees. So after 45 seconds, you find that the amplitude has decreased to 5.5 degrees. And this is because realistically, you're going to have air resistance acting on your pendulum and eating away the energy from it. So what we're going to do is calculate the damping coefficient, that's gamma. And then once we have that, we're going to find how long it takes for the amplitude to fall to 1% of its initial value. So pause the video, see if you can work this out, and then we'll go through it together. So I'm going to write down a few things that we derived dealing with damped harmonic motion. We're not necessarily going to use all of these, but I just want to sort of remind you of some things we derived. So the first is that the general solution for the motion acts as a function of time. It's not just a pure cosine function. Instead, it's given by A naught, which is our initial amplitude, times e to the minus gamma t. Gamma is our damping coefficient. And then times cosine omega prime times t. So A naught is our initial amplitude. So at t equals 0. Gamma is called our damping coefficient. And omega prime is the angular frequency, just like before, but with damping. So it takes on a different value when you have a damping force present. Omega prime is actually given by the square root of omega naught squared minus gamma squared, where omega naught is the frequency without damping. So what we're seeing here is with damping, the angular frequency decreases. The oscillation happens a little bit slower. Okay, so that's all the stuff we derived. Now, the part we really care about is this. If we look at our solution for x as a function of time, this piece right here, I'm just going to circle it, is the amplitude. Okay, whatever is in front of the cosine function is the amplitude. And what this is telling us is the amplitude decays over time. And it's given by a as a function of time is equal to that exact quantity I circled, a naught times e to the minus gamma t. Okay, so we can actually use this to solve for gamma, because if we start by dividing out a naught, we have a at time t divided by a naught. That equals e to the minus gamma t. But what I can do is take the natural log on both sides. So I have natural log a at time t divided by a naught is equal to the natural log of e to the minus gamma t. But when you take the natural log of e to the minus gamma t, that undoes the exponentiation, and you just get minus gamma t. So what we want to do, here, let's copy that down. Minus gamma t is equal to natural log amplitude at time t divided by initial amplitude a naught. We just need to divide out minus t, which gives us gamma equals minus natural log amplitude at time t divided by initial amplitude a naught divided by the time it takes. So here we go. We have gamma equals minus natural log. So the amplitude we reach is 5.5 degrees, but what we start with is 7.5 degrees. So that's the ratio I see inside the natural log, is 5.5 over 7.5. The units of degrees just go away. Now, on the bottom, I have the time it takes to reach that amplitude of 5.5 degrees, and we're given that this is 45 seconds. So that's what we're calculating. Minus natural log of 5.5 over 7.5, then divide that by 45. You get 0.00689 inverse seconds, which is, if we keep 2 sig figs on that, 6.9 10 to the minus 3 inverse seconds. So that's your gamma. That's your damping coefficient. Okay. Now let's actually take what I wrote down over here. Minus gamma times t is equal to natural log amplitude at time t divided by a naught. Let's rearrange that to solve for t this time. So t is equal to the natural log of the amplitude at time t divided by the initial amplitude a naught. We'll have a negative sign here, and then we'll divide out the gamma. So if the amplitude is 1% of the initial amplitude, that means this ratio in the natural log is 0.01. So if it's 1% as a fraction, that's 0.01. So we have minus the natural log of 0.01 over gamma, which we just calculated was 6.89 10 to the minus 3 inverse seconds. And because we have inverse seconds on the bottom, we just get seconds as a result of this. 668 seconds is what you'll get. So it takes 668 seconds for the amplitude to reach 1% of its initial value. So if we convert that to minutes, in every 1 minute, we have 60 seconds. So we're essentially dividing by 60, which gives us about 11 minutes. So it takes 11 minutes to reach 1% of the initial amplitude. And so here's a problem from the chapter 13 lecture on fluids. So your basketball has a mass of 575 grams when it's deflated. When it's inflated with air, your basketball has a radius of 11.7 centimeters. So if we have an inflated basketball, what downward force would you need to apply to completely submerge it in mercury? So the idea is if you just put the basketball in this bath full of mercury, it would float there. You would have to push down on it pretty hard in order to actually get it all the way underneath the surface of the mercury. So what we're going to find is how much force would you need to apply to actually hold it completely underneath the surface. So to work this out, we'll remember that air has a density of 1.23 kilograms per cubic meter. We're going to need to know that. And mercury has a density of 13.6 times 10 to the 3 kilograms per cubic meter. So pause the video for a second, see if you can work this out, and then we'll go through it together. Okay, so let's start by drawing a picture. So we have this container full of mercury, and we're imagining that you're pushing down on a basketball such that it goes all the way underneath the surface of the mercury like this. And you're just holding it there. So if we make a free body diagram of the ball, these are the forces that will be acting on it. So first we have the force of gravity, or the weight, acting on the ball. You're pushing down with some amount of force, so we have another downward force vector. Let's call that P, the force of your push. But we also have an upward force, which is actually very large, the force of buoyancy. Okay, so the mercury pushes up on the ball, making it want to float in this fluid. So if we apply F equals ma to the ball in the y direction, because all the forces are vertical, so we'll focus on the y direction. Net force in the y direction is equal to m times ay. Okay, so we have the buoyant force going up and the weight and the force of the push going down. So the buoyant force gets a positive sign minus the weight minus the push. That equals 0 because there's no motion. The idea is you're just holding the ball in a static position. So if we want to know what the force of the push is, that would just be the difference between the buoyant force and the weight, right? If I take the force of buoyancy minus the weight of the ball, then I've got the force of the push. Okay, so let's work that out. Well, remember that the force of buoyancy is given by the weight of displaced fluid. So by holding the ball underneath the surface of the mercury, we're displacing some of that mercury. So how can we calculate that? Well, that would be the mass of the mercury. So Hg is the chemical symbol for mercury. That's what we're using here. Times G. Okay, the mass of the mercury we displace times G is the weight. But let's also remember that density is equal to mass over volume. So the mass, or here, let's write this as rho equals m over v, right? That's density equals mass over volume. And the mass, therefore, is equal to the density rho times the volume v. So the buoyant force, therefore, would be the density of our mercury times the volume of mercury we displace, which is just equal to the volume of the ball because it's completely underneath the surface of the mercury, and then times g. So that would be the formula for the buoyant force. Okay, the weight is the force of gravity acting on the ball. So it has nothing to do with the mercury. This is just the force of gravity acting on the ball, which would be the total mass of the ball times g. We can actually split this up into two parts, right? Because we have the mass of the deflated ball, okay, with no air in it, plus the mass of the air. Okay, that would be the total mass of the ball. We have to take the mass of the deflated ball, just the rubber, plus the mass of the air that's inside, and then we multiply by g, and that's the weight of the ball. But, just like before, mass can be thought of as density times volume. So let's apply that to the air. We have the deflated mass plus the density of the air times the volume of the ball times g. Okay, so I think we're in good shape now. Let's put all of that into our equation for the push force. Remember, the push force is equal to B minus W, so it's equal to density of mercury times the volume of the ball times G. That's the buoyant force, B. We subtract the mass of the deflated ball plus the density of air times the volume of the ball times G. We could just plug the numbers in at this point, but I'm going to sort of rearrange things a little bit to make it a little easier to work with. So I have a term, I have two terms that have a common factor of the volume of the ball times G. So I have the density of the mercury minus the density of the air times the volume of the ball times G, and then minus the mass of the deflated ball times G. Okay? And then the last thing we'll note is that the ball is a sphere. So the formula for the volume of that ball is going to be 4/3 pi r cubed. Okay, so let's plug everything we know into the formula. So the push force is the density of the mercury, 13.6 times 10 to the 3 kilograms per cubic meter, minus the density of air, 1.23 kilograms per cubic meter, times the volume of the ball. That's 4/3 times pi times the radius cubed. So the radius we were given is 11.7 centimeters, or 0.117 meters, and then cube that, and then multiply by g, 9.8 meters per second squared. And then subtract the mass of the deflated ball, which is 557 grams, or 0.575 kilograms, times g, which is 9.8 meters per second squared. Now, unit-wise, what we're ending up with is kilograms times meters per second squared. And if you crunch the numbers, you'll get 888.4. But here we want to keep 3 sig figs. So we have 888 newtons of force. That's how hard you'd have to push down on this ball in order to completely submerge it in the mercury. All right, let's try this one out. So water enters a garden hose, which has a circular cross-section with a diameter of 1.6 centimeters. So that's the cross-section of the hose over here. The water in the hose has a speed of 3 meters per second. So there's a nozzle with a diameter of 0.500 centimeters attached to the end of the hose. So basically this is a much narrower cross-section at the nozzle. So based on that, what is the speed of the water coming out of the nozzle? We'll find that speed in meters per second. We'll also find the volumetric flow rate of the water coming out of the nozzle in centimeters cubed per second. Then finally, how long in seconds would it take to fill up a cylindrical bucket with a diameter of 12 centimeters this way and a height of 17.5 centimeters this way if we're using this hose to fill it up? So pause the video, try to work this out, and then we'll go through it together. Okay, so if we want to find the speed of this water coming out of the hose, what we can use is the continuity equation. And let me just remind you what this says. This says that the volumetric flow rate, which is given by R, is equal to A, that's the cross-sectional area of this hose, times V. And that is a constant. So in other words, let's call this part of the hose back here point number 1. And then let's call the nozzle where the water is coming out point number 2. By saying the volumetric flow rate is constant, it's the same at point 1 and 2. What we're saying is A1 times V1 is equal to A2 times V2, where those are the cross-sectional areas at those 2 points. So what we'd like to do is find V2. That's equal to A1 divided by A2 times V1. So we're talking about circular cross-sections. Circular cross-sections, meaning the area is pi times r squared, or since what we're given is diameters, pi times d over 2 squared, because the radius is equivalent to half the diameter. So we have pi times d1 over 2 squared divided by pi times d2 over 2 squared times v1. So canceling out the factors of pi and 2, we have d1 over d2 squared times v1. So the ratio of the areas is the same as the ratio of the diameters squared. Okay, so the diameter at point 1 is 1.6 centimeters. The diameter at point 2 is 0.500 centimeters, and we're going to square that and multiply by the speed of the fluid at point 1, which is 3 meters per second. So this gives us the speed of the fluid at point 2. That's the speed of the fluid coming out of the nozzle, which is 30.72 meters per second. So the centimeters here cancel. We're just left with meters per second. So keeping 3 sig figs, that's 30.7 meters per second. So it's coming out of the nozzle really, really fast because we've narrowed the cross-sectional area to such a small amount. Okay. Now, remember, at the very beginning we said the volumetric flow rate is equal to A times V. And I can make this calculation at point 1, or I can make this calculation at point 2. It doesn't matter. I'm going to get the same result because it's a constant flow rate. So, I don't know, how about we pick point 1? Let's do A1, V1 to get the volumetric flow rate. So again, The area is pi times diameter over 2 all squared, and that's times V1. So we have a quarter. It's 1 over 2 squared is a quarter times pi d1 squared times V1. So we have 1/4 of, so the diameter at point 1 we were given is, we were given this to be 1.60, and that's in centimeters, and we're going to square that. And then V is 30.7 meters per second. But if we convert that to centimeters per second, that would be the same as multiplying by 10 to the 2. So we have 30.7 times 10 to the 2 centimeters per second as the speed at V1. So you crunch these numbers and you should get 603 centimeters cubed per second. That is the volumetric flow rate. So every single second that passes, you have 603 cubic centimeters of water coming out of the nozzle. Okay, so lastly, we're going to remember that the volumetric flow rate, here, let me just write this in words. Volumetric flow rate is equal to the volume of fluid that's passing through the hose per unit time. In other words, R is just equal to capital V for volume divided by T for time. So if I want the time, that would be the volume divided by the flow rate. So if you think about this for a second, if I want the time that it takes to fill up the entire bucket, I should be using the volume of the bucket here. So what is the volume of the bucket? That's, well, it's a cylindrical bucket. And the volume of the cylinder is given by pi. Here, let's write it down. Pi times the radius squared times the height. Where this is the radius, this is the height. Now, we're given the diameter of the bucket. That's 12.5 centimeters, so we'll divide by 2 to get the radius, square it, multiply by the height, which is 17.5 centimeters, and now we have the volume of the bucket. Divide by the flow rate, 603 centimeters cubed per second, and now what we have is the time measured in seconds that it takes to fill up the bucket. And this should work out to 3.56 seconds. So the flow rate is pretty fast. So it's able to fill up the bucket in a very short amount of time. It takes 3.56 seconds to do that. So let's do another one from the chapter 13 lecture. Here we have a sealed cylindrical container of water, which has a spout, which is 15 centimeters below the water line. So this is the container. It's completely sealed off, so it's not open to the air. And the water level is shown right here with the dashed line. So the spout is 15 centimeters below that. The water is kept under pressure to make it come out of the spout faster. So the air up here on top of the water is greater than just atmospheric pressure. And that makes the water come out of the spout faster. Okay, the diameter of the container itself is 19 centimeters in this direction, and the diameter of the spout is 1.5 centimeters over here. What you want to happen is you want the water to come out of the spout at a flow rate of 835 cubic centimeters per second. So again, every second that passes, we want 835 cubic centimeters of water to be coming out. So if we want to achieve this, what should the pressure of the air above the water be to get this flow rate? So what kind of pressure do I need up here in units of atmospheres to get this all to work out? So pause the video, try to work it out, and then we'll go through it together. Okay, so first we're going to label two different points in the fluid. Let's let point 1 be the water at the top of the container. So this is point 1 right here. And then we'll let point 2 be the water coming out of the spout. So point 2 is right down here. Now we can relate what's going on at point 1 and point 2 with two different equations. We have the continuity equation that we saw earlier. So this says A1 V1 equals A2 V2, which is equal to the flow rate R. We also have Bernoulli's equation. And this relates what's going on at point 1 and point 2. P1 plus 1/2 times rho times V1 squared plus rho times G times Y1 is equal to P2 plus 1/2 times rho times V2 squared plus rho G Y2. Okay? So we're going to use both of these equations together, but what we're really trying to solve for is P1. I want to know what that pressure is of the fluid at the very top of the container. So P1, if we solve for it, is going to be P2. I'll have that pressure 2 on the other side. And then I'll have two terms in my equation with 1/2 times rho times V squared. I'll have a V2 squared, and then I'll subtract off the V1 squared. Then I'll have rho times G times Y2 minus Y1. All right? So what do we know about all of these different variables? Because I want to solve for P1. Well, I know that P2 is atmospheric pressure because the fluid coming out of the spout is open to the atmosphere. Okay, it's in contact with the atmosphere. So this would be 1 atmosphere, or 1.013 times 10 to the 5 pascals in terms of the pressure. Rho, that's the density of the fluid. We're talking about water here, so that's 1.00 10 to the 3 kilograms per cubic meter. What about Y2 minus Y1? So it's the height of the fluid at point 2 minus the height of the fluid at point 1. Well, that's going to be negative 15 centimeters, or negative 0.150 meters. Okay, it's negative because point 2 is below point 1, but the distance is 15 centimeters. Okay, so it looks like the last piece of information here, oh yeah, and then of course G is 9.8 meters per second squared, but after that, the last piece of information we're going to need to know is V2 and V1. So let's work that out using the equation of continuity. So using the equation of continuity, we can see that V1 is equal to the volumetric flow rate R divided by A1. And in a similar way, V2 is the volumetric flow rate R divided by the area A2. So, okay, if we're talking about point 1, the volumetric flow rate is actually the same as at point 2. That's going to be constant throughout the fluid. So R is 835 cubic centimeters per second. And then we divide that by the area at point 1. So here, let's think about this. The cross-sectional area at point 1 would be this big circular area. That would be our A1. So that would be pi r squared, or pi times the diameter over 2. 19 centimeters is the diameter over 2, and then square that. So the units will end up being centimeters per second when we do this calculation. And for V1, you're going to get 2.945 centimeters per second. If we convert that to meters per second, that's 0.02945 meters per second. And then we'll keep 3 sig figs. Okay, for the speed of the fluid at point 2, it's the same flow rate, 835 cubic centimeters per second, divided by the cross-sectional area over here. So the circular area of the spout right here is what we're interested in for A2. And that's going to be pi r squared again. But this time the radius is 1.5 centimeters over 2. So we square that. So just to be clear, A is equal to pi r squared for both of these circular cross sections. Okay, so if you crunch those numbers, you get 472.5 centimeters per second. That's how the units will work out here. But in meters per second, that would be 4.725 meters per second. So now we have everything we need to solve for P1. Let me just put the equation in brackets right here, okay? Everything in that admittedly pretty complicated expression, we have a numerical value for it, so we can actually calculate P1. So here we go. P1, that's equal to P2, which is 1.013 times 10 to the 5 pascals. Then I add that to 1/2 times the density rho is 1.00, 10 to the 3 kilograms per cubic meter. And then I have V2 squared minus V1 squared, so 4.725 meters per second squared minus 0.02945 meters per second, square that as well. And then I have plus rho, which again is 1.00, 10 to the 3 kilograms per cubic meter, multiplied by 9.8 meters per second squared, and then multiplied by y2 minus y1, which is negative 0.150 meters. So my writing got a little small, but that's what everything looks like when we plug it in. So if you crunch those numbers in your calculator, you're going to get 1.1099 10 to the 5 pascals. And we'll keep 3 sig figs on that. So to be clear about the units here, what I did is I plugged everything in with SI units. So what came out was the SI unit of pressure. If you analyze the units, you'll see it does work out in pascals. But let's take that and convert it to atmospheres. So we have 1.1099 10 to the 5 pascals. In every 1 atmosphere, we have 1.013 times 10 to the 5 pascals of pressure. Pascals will cancel. And so this will work out to 1.10 atmospheres. In other words, if you pressurize this container a little bit, so it has greater than atmospheric pressure up here, you can get the fluid to come out faster. And that's basically how a standard beer keg works. Okay, so let's do an example from chapter 17 on thermal expansion. So at negative 10 degrees Celsius, the mercury in a thermometer completely fills a spherical cavity of radius 0.350 centimeters at the bottom of a glass tube. So this is the thermometer. This is what it looks like at negative 10 degrees Celsius. The mercury in the thermometer is completely filling this spherical cavity at the bottom of the tube, but none of it has actually gone up into the tube yet. So the coefficient of volume expansion for mercury is beta equals 1.82 times 10 to the minus 4 inverse degrees Celsius. We're going to calculate the increase in volume of the mercury if the temperature rises to positive 30 degrees Celsius. So we know that the mercury will expand if the temperature goes up, and we're going to find the increase in volume as a result of that. Also, the diameter d of this glass tube is 0.00450 centimeters. So we're going to find the height of the mercury in the glass tube when the temperature is 30 degrees Celsius. So again, the idea is all of the mercury is confined to this spherical cavity when the temperature is very low. When the temperature rises, the mercury will expand and it will go up into this tube. We're going to find the height of the mercury in the tube when the temperature is 30 degrees Celsius. So as you do this, neglect the expansion of the glass. So assume the mercury is expanding, but the glass is not. So pause the video, try to work this out, and then we'll go through it together. Okay, so first we'll write down a result that we derived in lecture. For volume expansion, we have delta V, the change in volume, is equal to 3 times alpha times V naught times delta T. Now alpha is what we call our coefficient of linear expansion. Beta is what we call our coefficient of volume expansion. And beta is equal to 3 times alpha. So delta V can also be just written as beta times V naught times delta T. Okay, well, the initial volume of the mercury is equal to the volume of the sphere. It's the volume of the spherical cavity that it fills up. So that's given by 4/3 times pi times r cubed. So delta V, the change in volume that the mercury undergoes if its temperature changes, is going to be given by beta, which is 1.82 times 10 to the minus 4 inverse degrees Celsius. And then V naught, that's the initial volume when the mercury is only in the spherical cavity. That's 4/3 pi times the radius, which we were given as 0.350 centimeters. And we'll cube that. And then we have delta T, which is the temperature change. So we end up at 30 degrees Celsius, but we start at negative 10 degrees Celsius. That's our delta T. 30 minus negative 10 degrees Celsius. So unit-wise, we're going to cancel out degrees Celsius and only be left with centimeters cubed. And this works out to 1.31 times 10 to the minus 3 cubic centimeters. Okay, that's the increase in volume of the mercury as the temperature goes from negative 10 degrees Celsius to 30 degrees Celsius. So actually, let's draw that on our diagram. So the mercury that was initially only in the spherical cavity at the bottom, after it expands, some of it goes into this tube here. Okay, so let's shade this region right here. This is our delta V. And so there's a height to this column of mercury in the tube. We'll call that H. So here, let's really think about this carefully. Delta V, this extra volume of mercury, is the volume that goes into the cylindrical tube. So the volume of that cylindrical tube is equal to pi times the radius of the tube. So here, we're using d for the diameter of the tube. The radius would be d over 2. We square that, and then multiply by h. That's the formula for the volume of the cylinder. So this is 1/4 times pi times d squared times h. And we're trying to find h. So what we'll do is solve for h. That's going to be 4 times delta V divided by pi times d squared. So we have 4. Delta V is 1.31, 10 to the minus 3 cubic centimeters. And we're going to divide that by pi times the diameter of the tube, which is 0.00450 centimeters, and square that. And if you crunch those numbers, you'll get 82.4 centimeters. So the mercury rises to a height of 82.4 centimeters in the tube as the temperature increases. And so what we're illustrating here is just the operating principle behind a mercury thermometer. As the temperature increases, the volume of the mercury expands, and so it goes to a higher level in the tube. And we can read out the temperature based on the height of mercury in the tube. So that's going to be it for this video. I think we've done enough practice problems for now. So please continue to take a look at these practice problems at the end of each lecture as you study for the test. These will be very useful as you study. So we'll end this video here. I'll see you in the next one. And as always, take care, be safe out there, be healthy. See you later.